Welcome to The Explainer. Today, we are pulling back the curtain on one single rule from calculus that, believe it or not, has become the engine behind modern artificial intelligence. It's called the chain rule, and we're about to find out how a concept from the 1600s is literally powering the tech of tomorrow. All right, so here's our game plan. We're going to start with the basic idea of one process feeding into another. Then we'll get into the mechanics of the rule itself, see how it actually works. And then, the big finale, we'll reveal its absolutely incredible impact on AI. So first things first. Before we even look at a formula, let's talk about the core problem that needed a solution in the first place. This right here, this is the whole puzzle. What do you do when one process's result becomes another process's starting point? How do you measure the rate of change for the entire system when all its parts are linked together like that? And this slide, it's the perfect way to picture it. Just imagine the first block, f of x, takes in something and does its job. Then, whatever comes out of it gets fed directly into the second block, g of x. They're chained together. This is literally the chain in the chain rule. Now, in the world of math, this has a formal name, a composite function. When you see it written out like g of f of x, all you have to remember is you work from the inside out. You figure out f of x first, and then whatever that answer is, you plug it into g. So we've got these nested functions. The big question is, how in the world do we find their rate of change, their derivative? Well, this is where the chain rule steps in, and it is such an elegant solution. Now, you'll see the rule written a couple of different ways. The one on the left, that's called Leibniz notation, and it's fantastic for theory. But for actually using the rule, for getting your hands dirty, the prime notation on the right is just way more intuitive. So we're going to stick with that one. Okay, I get it. This formula might look a little intimidating at first glance. But the beauty of it is that it's not really a complex idea. It's just a recipe. It's a set of instructions that breaks a tricky problem down into a really simple, repeatable process. You can think of it like a three-step dance. First, you take the derivative of the outside function, but, and this is key, you leave the inside function completely alone. Just leave it as is. Then you multiply that whole thing by the derivative of the inside function. That's it. Outside, then inside. Theory is one thing, but let's make this real. Seeing the rule in action is where it's all going to click into place. Okay, let's walk through this one together. We've got y equals cosine of x cubed. So, following our steps, what's the outer function? Well, that's the cosine part. Its derivative is negative sine. Got it. Now, what's the inner function? That's x cubed, and its derivative is 3x squared. Easy enough. Now we just assemble the pieces. We take the derivative of the outer part, negative sine, and we keep the original inner part, which gives us negative sine of x cubed. Last step, we multiply by the derivative of the inner part, 3x squared, and boom, there's our answer. So why do we even need this rule? I mean, couldn't we just do it the long way? Well, this slide puts it perfectly. To solve this problem without the chain rule, you would have to multiply that big term by itself 17 times. Yeah, the alternative isn't just a different rule, it's a pain rule. But here's the thing. The real power, the real magic of the chain rule isn't just for handling two functions. It's that the same logic scales up beautifully to handle way more complex systems. What if you have a function inside another function? No problem. You just keep applying the same rule over and over. You start with the derivative of the outermost layer, then multiply by the derivative of the next layer in, and you just keep going until you get to the very center. The chain just gets longer. And this is where it gets really powerful. The same idea works even when you have tons of different inputs and variables. You can actually map it all out like a tree, tracing how every single little input branches out and affects the final result. You're going to want to keep this image in your head because it looks an awful lot like a neural network, doesn't it? And that brings us to the big payoff. This is it. All this math, these nested functions, these derivatives, it all leads directly into the engine room of modern artificial intelligence. This quote really just nails it. Deep learning isn't just using the chain rule, it's using it to an extreme. Those incredible models that can generate images from text or translate languages in real time, they are built on this exact idea of having many, many levels of functions all composed together. At the end of the day, a neural network is really just a giant, massive composite function. Each layer in that network is its own function that takes the output from the layer before it and uses it as an input. An image, a piece of text, whatever, it goes through dozens, sometimes hundreds, of these nested layers before you get a final answer. So, the billion-dollar question. How does an AI actually get smarter? How does it learn? It uses an algorithm called backpropagation. And at its very core, what is backpropagation? It is just a massive, incredibly clever application of the chain rule. It's what allows the AI to look at its final mistake and calculate exactly how much every single one of its millions of internal settings contributed to that error, all the way back to the start of the chain. Let that sink in for a second. When an AI makes a mistake, the chain rule gives it a mathematical roadmap to trace that error backwards through every single connection. It tells the network precisely how to adjust each of its millions of parameters layer by layer so it can do a better job next time. The chain rule isn't just some dusty old formula. For AI, it is the very engine of learning. It's pretty incredible, right? We started with a simple rule for nested functions, and we ended up with a method for machines to learn. It just leaves you wondering, what other complex systems out there, in biology, in economics, maybe even in our own minds, are just waiting to be understood by carefully breaking them down link by link?